Welcome to The Explainer. Now today, we're not going to be looking up at the stars for proof of our planet's shape. Instead, we're going to get our hands dirty, digging into the dirt, the concrete, and the everyday work of land surveyors to uncover this really elegant mathematical proof that's hidden right under our feet. So, let's just dive right into it with a question that seems pretty simple, but, it hints at a much, much bigger reality. We build these massive structures that look perfectly straight, but the secret, the thing surveyors have to deal with every single day, is that building truly straight is impossible on a world that isn't.
And this brings us to the fundamental puzzle that surveyors and engineers have to solve. How in the world do you build these massive, incredibly precise structures on a surface that just refuses to lie flat?
I mean, think about it like this. For a small project, say a fence in your backyard, you can totally get away with assuming the world is flat. No problem. But the second you scale that up to a highway or a tunnel or a high-speed rail line, that assumption completely breaks down. The errors start piling up, and all of a sudden your two ends, they just won't meet in the middle.
A perfect example of this is a piece of technology we all use every day, GPS. It is fundamentally built on a non-flat foundation. Its very existence is a testament to a curved Earth.
Right at the heart of the GPS in your phone is a mathematical model called WGS84. And what it does is define the Earth not as a perfect sphere, but as an ellipsoid. Just think of a ball that's been kind of squished slightly at the poles and bulges out at the equator. Now, this isn't a guess. It's the essential reference map that makes the whole global positioning thing even work.
And the process itself proves the point. Your phone is listening for signals from satellites that are orbiting a massive curved body. It's solving this really complex 3D geometry problem just to pinpoint where you are. If the Earth were flat, the math would just completely collapse, and the entire system would fail. It's as simple as that.
So this creates a really practical problem, right? GPS gives you a precise point on a giant globe, but construction crews need a flat blueprint. So how do you translate that curved reality onto a flat piece of paper for a local project? Well, the answer is map projection.
And this is where surveyors use two totally different systems. On the left, you've got the global 3D coordinate system from your GPS, the big picture. And on the right is the local 2D state plane system that's used for the actual construction on the ground. A huge part of a surveyor's job is constantly translating between these two worlds.
And here's the kicker, the really counterintuitive part. The fact that these complex local maps even exist is proof the Earth isn't flat. Think about it. If it were flat, you'd just need one giant grid for the whole world. The very fact that we need thousands of these unique local projections, that is the ultimate proof of the curve.
But this process, this act of flattening the curve, it leaves behind a smoking gun. It's a kind of mathematical fingerprint, hidden in every single local map, that proves the global curve exists. This all points to an unavoidable consequence of mapmaking. You simply cannot represent a curved surface on a flat one without some kind of distortion. A little bit of stretching here, some squishing there, and this predictable error is exactly what surveyors have to calculate and correct for every day.
Okay, so what exactly is this distortion? And why is it the key that basically unlocks this whole puzzle?
Well, here's what it boils down to. On our curved Earth, a mile that you measure on the actual ground is not exactly equal to a mile that you measure on the flat projected map. There's a tiny but predictable difference. If the Earth were flat, they would match up perfectly, every single time. No questions asked. So, to fix this, surveyors use what's called a scale factor, a really precise number, kind of like this one. They multiply the distance on the ground by this factor to get the correct distance on the map, or they do it the other way around. It's basically the conversion key between the real curved world and the flat blueprint. And ultimately, the very existence of this tool, this scale factor, is just undeniable proof. It's used on every large project for one reason and one reason only, because the Earth is curved. You just don't need a tool to fix a problem that doesn't exist. Okay, so this isn't just about theory and math on a blackboard. Surveyors actually observe and measure the curve's effect every single day with simple, repeatable experiments right on the ground using tools that have been around for centuries.
So let's look at the first experiment. A surveyor runs a really precise level line over a long distance. If they don't correct for the Earth's curvature, their elevations will start to drift downwards, consistently. the endpoint will look lower than it actually is, because their line of sight is going straight out into space, while the Earth is curving away right underneath it.
And what's so powerful here is that the error isn't random. It grows in a perfectly predictable way that matches the exact geometry of a sphere with a radius of about 3,959 miles. The math that they use to correct this error only works because our model of the Earth is correct.
Now, a second test, which is considered a gold standard, is even more elegant. You measure the elevation changes in a big triangle, going from point A to B, then B to C, and then all the way back to A. On a flat plane, you should end up exactly where you started. The sum of all those changes should be 0. But in reality, it never is. The loop doesn't close, and that proves the 3 points exist on a curved surface.
So why does all of this matter? What would actually happen if surveyors and engineers just ignored this whole reality and decided to work on a flat plane?
Well, in short, our modern world would just fall apart. GPS would be completely useless. Long bridges would miss their mark in the middle. Property lines would be an absolute chaotic mess. The entire foundation of modern infrastructure relies on acknowledging and correcting for the Earth's curve.
And this really is the bottom line. For the professionals who actually build our world, this isn't some philosophical debate or a matter of belief. It's a practical, it's a measurable, and frankly, it's a billable reality. The curvature is a problem they have to solve every single day to do their job correctly.
And that leaves us with a really powerful final thought. In the world of surveying, you just don't argue at the math, especially when applying a specific correction consistently fixes your errors and makes your measurements close perfectly. The numbers don't lie. So the question isn't whether the Earth is curved, but how we become so clever at managing to build on it anyway.